Okay, now we're going to go over turbulent boundary layers, at least a little bit. Okay, and so here we're just going to go over the basic characteristics of them and some of the basic results. Unfortunately, unlike laminar boundary layers, there is no nice pen and paper theory where we can use to get a nice analytical solution like we did for the laminar boundary layer. But any boundary layer, whether it's turbulent or not, the turbulence takes some distance to form. So if you consider a flat plate, and the flat plate is either very long or the flow is very high speed, the initial boundary layer on the flat plate will initially be laminar. Then at some critical distance, I'm going to call that XCR. Oops. Let me redraw that. X critical for X critical. The boundary layer will transition into turbulence. And this would be turbulent. Where even in the boundary layer here, in the laminar section, the streamlines would be nice and straight, without any chaotic motions. But in the turbulent section, there's a lot of chaotic motion in the boundary layer, just like in the pipe flow. Okay, and this chaotic motion really it really changes things. And so, and in fact, what this does is you could imagine there's a big old vortex, say here, and there is very high momentum, basically high momentum fluid that is flowing in the free stream. Well, this vortex can go up and grab some of that and basically pull it down. And when it pulls that high velocity fluid downwards, it basically tosses it down close to the flat plate. And a consequence of that is if we qualitatively compare the velocity profile, this is U over cap U. For a laminar boundary layer, it'll look something like this. This would be Y. And for a turbulent boundary layer, it would look something like this. Would be much flatter, with a much sharper gradient, near the wall. So this would be U bar turbulent. Because remember, for a turbulent flow, U equals U bar plus U prime. Okay, and so basically U prime is represented by basically all these random little vortices that are basically jiggling these streamlines. The streamlines would look something like that. That are basically jiggling the streamlines. I don't know why this thing keeps doing that, but it does. And then basically what all these vortexes do by transferring some of the high momentum fluid down closer to the flat plate is it basically squashes the mean velocity profile down to where du bar dy is greater for turbulent, is greater than du dy for laminar at y equals 0. Okay, so this basically means that the shear stress for a turbulent boundary layer is going to be much higher than it is for a laminar boundary layer. So the skin friction drag for a turbulent boundary layer is always higher than it is for a turbulent boundary layer than it is for a laminar boundary layer. Okay, and this critical transition distance is defined by an RE transition, and that equals U XCR over nu. And for the purposes here, there are different definitions for that. It is 5 times 10 to the 5th. So for external flows, the exact Reynolds number that causes the transition to turbulence is not 2300. The 2300 is specific to internal pipe flow. The exact Reynolds number that causes the transition to turbulence is dependent on the configuration. So for a flat plate that's perfectly smooth, a perfect flat plate, it is roughly 5 times 10 to the 5th. Okay? And then in the turbulent boundary layer, and I'll call that TBL. In the TBL, the boundary layer height delta x, or delta divided by x, is approximately 0.37 over the Reynolds number based on x to the 1/5 power. And so, and that implies that delta, if you work through the math if you work through the algebra on REX, what you find is that delta is proportional to x to the 4/5 power. So the BL grows much faster, or a turbulent boundary layer grows much faster than a laminar boundary layer. And if I scroll back up to the little cartoon here, that's because basically just as I have basically similar to the high momentum basically fluid being tossed down from above by a vortex, and it's being tossed down closer to the flat plate, there is another counter rotating vortex that is taking some of the slow fluid close to the flat plate and then basically tossing it up. And this act of tossing it up basically helps to thicken the boundary layer and then make it grow faster. Okay? And recall that in LBL grew by x to the 1/2 power. Okay? So a much higher power. Okay, and the drag coefficient, there are multiple. There's no one unified theory of turbulence. In fact, as I said before, turbulence is one of the basic unsolved questions in all of physics still, and so there's no unified theory for it. And because of that, there are all kinds of semi-empirical and empirical relations for the drag coefficient. And so I'm just going to scribble down 2 of them. And so here the drag coefficient equals 0.0742 over REL to the 1/5 power. And this relation is valid for RE, or for 5 times 10 to the 5th is less than REL is less than 10 to the 7th. Okay, and this comes from assuming the 1/7 power law of velocity profile. It's the same profile. It's the same 1/7 profile that we worked with in the pipe flow. And so if you basically assume that as the mean velocity profile for U bar, then you can integrate the shear stress, apply it with some very simplified turbulence theories, and you wind up getting this. Okay, but this is only accurate up to about Reynolds number of 10 to the 7. And of course, it is not valid below a Reynolds number based on length of 5 times 10 to the 5th, because then the boundary layer is laminar. Okay, and there's a more empirical one. And so this would be, there's an empirical one, so that's CD equals 0.455 over log base 10 of the Reynolds number based on length, and that raised to the 2.58 power. And this is empirical, meaning it's just a curve fit to data for the most part. And this is valid from 5 times 10 to the 5th is less than REL is less than 10 to the 9. Okay, so it's because this is a better fit to data. It is this bottom one. Oops, wrong one. This this bottom relation here is more applicable. And so, what do we do if the boundary layer is both laminar and turbulent? Okay, and so what do we do about that? Because these relations here assume that the entire boundary layer is turbulent. Oops, sorry, I hit the wrong button again. Assumes the entire BL is turbulent. But a substantial portion of the boundary layer, in some cases, might be laminar. Because remember, it takes some distance for the boundary layer to transition into turbulence. Okay, and this distance here is XCR. Okay, so essentially what we want to do then, when we compute the drag force, is that the drag equals the integral from 0 to the transition distance using tau wall for the laminar case, dx, plus the integral from x critical to the entire length of tau wall in the turbulent section, dx. Okay, and we can find, and to do that we need to find XCR. Well, remember that the Reynolds number at the turbulent transition for a flat plate boundary layer is equal to rho times cap u x critical over mu. Need to get away from this little page upper button here. And if you solve that for XCR, XCR is equal to the Reynolds number at transition times the viscosity divided by rho times cap u. And so if we recall that tau wall equals that the integral of tau wall recall that the integral of tau wall from 0 to some x dx is equal to 1/2 rho u squared CD times x. Okay, and again, we're assuming unit depth. Okay, so we can use the drag coefficient to evaluate this, and we can break. So we can which we can do the integral based on integrating the Welsh shear stress using the drag coefficient, which already has it integrated, but this drag coefficient is based on the integral from 0 to some length. But here we have an integral from the transition distance to some length. So what we need to do is we need to rewrite this integral into a form that is useful for the drag coefficient. So we'll do that. So the integral from xcr to L of tau wall, and this is turb for turbulent, dx equals the integral from 0 to L of tau wall for the turbulent dx, and we've taken too much now. Now we need to subtract the integral from 0 to x critical of tau wall for the turbulent side of the boundary layer dx. Okay. And then this piece here just turns into 1/2 rho times cap u squared times CD for the turbulent evaluated at L times the length, and this becomes 1/2 rho u squared times the drag coefficient using the turbulent relation evaluated at the critical transition point times XCR. Okay. And so piecing piecing everything together and adding this laminar section here, we have that the drag force is equal to 1/2 rho times cap u squared, because that's common to all of them, times the laminar piece, times the drag coefficient for the laminar, evaluated at the transition Reynolds number, times x critical, plus the drag coefficient for the turbulent evaluated at REL times the plate length minus CD for the turbulent boundary layer evaluated at the transition Reynolds number times the critical transition distance, and if we substitute in XCR from up here, XCR from up there and apply that the same thing to here and simplify, we get that the drag force, again just applying some algebra, is 1/2 rho times the free stream velocity squared times L times the drag coefficient for the turbulent portion evaluated at L or REL, whichever you prefer, plus the transition Reynolds number times the viscosity over rho times the free stream velocity times the drag coefficient for the laminar piece evaluated at I better be consistent, evaluated at the critical distance, which would be RE transition, if you want to think of it like that, minus CD for the turbulent portion, evaluated at the critical transition distance, which again would be RE transition, which is what you would put in the drag correlation, times 1/2 rho U squared. Okay. Then simplifying, we have CD equals drag over 1/2 rho U squared times L. Again, we're assuming unit depth. Okay. Then, doing that, the drag coefficient, I'm going to take this whole thing and just copy it. Then CD equals this entire thing. I'm going to get rid of these. Divided by 1/2 rho U squared. Okay, times L. Okay, and so the 1/2 rho U squared here cancels out, and the 1/2 rho U squared here cancels out. This L cancels out, but over here we don't have an L, because this is evaluated at the critical transition distance, not L, and so if we simplify this out, this becomes equals CD for the turbulent portion evaluated at L plus the transition Reynolds number times mu over rho U times L. Well, this parameter here is just 1 over REL times the drag coefficient for the laminar section evaluated at the transition distance minus the drag coefficient for the turbulent section evaluated at the critical transition distance. Okay, then we find that CD equals CD for the turbulent section based on REL plus RE transition over REL times CD for the laminar piece evaluated at the transition Reynolds number minus CD for the drag coefficient for the turbulent piece evaluated at the transition Reynolds number. Okay. So basically what this is doing is this is adding the drag coefficient for the entire turbulent plate, subtracting off the turbulent drag from the laminar section, and then adding the actual drag from the laminar boundary layer profile. So if we use RE transition equals 5 times 10 to the 5th, and there are different definitions for it, and CD for the turbulent equals 0.0742 over REL to the 1/5, we wind up with that CD is equal to 0.0742 over REL to the 1/5 power minus 1748 over REL. And the 1748 over REL is just evaluating this. Okay? And that just turns out to be a number. Okay, and this is valid for 5 times 10 to the 5th is less than REL is less than 10 to the 7. Okay, and if you use the other CD for the turbulent equals 0.455 over log 10 REL to the 2.58, that implies you'll have CD is equal to 0.455 over log base 10 of REL to the 2.58 power minus 16 10, it looks like, over square root of REL. Is that right? Let me look at that real quick just to make sure. Okay, thought that looked wrong. That's 1610 over REL. Okay. And this is valid if 5 times 10 to the 5th is less than REL is less than 10 to the 9. So when you use these correlations, make sure you check your Reynolds number, which you need to calculate anyways to use these. Make sure that if the Reynolds number is 8 times 10 to the 8, that you don't use this relation here, it will be invalid. Okay, and so you need to check which relation that you are going to use. And so that would be a turbulent flat plate. And so now there are lots of things that affect boundary layers, and I'll just go over one of them, and that's the effect of pressure gradients on a boundary layer. And for this purposes, it does not matter whether it is laminar or turbulent. Just recall that the pressure on a boundary layer is imposed by inviscid of flow region outside. Okay. Okay, and just recall that in this vertical strip here, the pressure is a function of x, and it is not equal to a function of y. And so the pressure is imposed in the boundary layer by the inviscid flow above it. Now, what if the pressure here is what if the pressure is equal to a function of x? What effect does that have on the boundary layer? I can guarantee you for these flat plates, as I've drawn here, a dp dx is equal to 0. But what if we have a flat plate inside of a contoured nozzle? Okay, so say I have a nozzle assembly, or a nozzle diffuser assembly, where the nozzle portion, or the portion that accelerates the flow, looks like this. There's a flat section, and there's a diffuser. And just recall from thermo, and even earlier in this class, that a diffuser decelerates the flow. And a nozzle accelerates the flow. Okay, and so we'll just assume that we have some u. Well, in this region here, where we are accelerating the flow, u of this would be x. U of x is increasing, and then because this is the inviscid core, Bernoulli is valid, which means that P of x decreases. And so what this is called, if P is decreasing in the direction of U, that is called a favorable pressure gradient. Okay, and essentially what you can sort of think of that as is we have a boundary layer here, and the pressure here is imposed, is basically constant, but the pressure here is higher than the pressure over here. So what that basically means is that for a fluid element in the boundary layer, there is a net pressure force that is accelerating it in the direction of the flow. So it's actually speeding the flow up in the boundary layer. And what happens in these favorable pressure gradients is that it actually pushes the boundary layer a bit flatter, and the velocity gradient becomes much steeper. Which implies that tau wall increases if the P gradient is favorable. Okay. Now, in this region here, dp dx is equal to 0. That's a really bad d. Let me fix that. dp dx is equal to 0. So here the boundary layer just grows as it normally does. Now, in this region here, we are increasing the area in the direction of the flow, and if we assume incompressible flow, then what happens is u of x decreases as x increases. Basically, as we go further downstream in this diffuser, the velocity goes down, which means P of x by Bernoulli will increase. And what happens is that actually causes the boundary layer to go, in the beginning, to grow faster. And if we think of this thin strip here, now what happens is we have a higher pressure on the right side than we do on the left, but yet the flow, U, is going that way. So then what happens is basically now the pressure gradient is fighting the flow in the boundary layer. Whereas over here, the pressure was assisting the flow in the boundary layer. Here it's actually fighting the flow in the boundary layer. And at the very least what happens is basically you can think of it as pushing against the boundary layer, and it starts to flatten the velocity gradient near the surface of the object like this, so it becomes much more shallow. Goes down, which that means there is less, which means that the shear stress is significantly less. But what can happen if the pressure gradient is way too high? What happens is the flow can actually separate, and so when that happens, we'll delete this and delete this. What happens, and I'll make the diffuser a bit longer, and then what happens, oops, wrong one. What happens is that eventually that the pressure forces push so hard on the slow-moving fluid at the bottom of the boundary layer that they basically stop it. And what happens is the velocity gradient is that the velocity profile starts to look like this. And this here, we have du dy equals 0. And that occurs right here, and this is called a separation point. And it's called a separation point because the boundary layer here is no longer attached to the wall. It's really no longer a boundary layer. And what happens is, if we go downstream of this, is that the flow in a portion of the boundary layer is actually going in the reverse direction. Is that these pressure forces have pushed so hard to the right against the flow that they've actually forced it to go backwards. And so the velocity profile starts to look like this. Okay, and this is called reverse flow. Okay, and that's typically bad. You almost never want reversed flow. Okay, and so you just need to be aware of that these things occur, and that you need to contour nozzles and diffusers very smoothly to avoid these adverse effects of them. And in extreme scenarios, unfavorable pressure gradients can cause aerodynamic stall. Okay, and so basically what that means is, if I have an airfoil and it's at some angle of attack, like that, it's pretty bad airfoil. And I have some free stream velocity u, and I'll have some sort of this is the airfoil. Is in this section here, I'll have a favorable pressure gradient, and in this region here, I'll have an unfavorable pressure gradient. Okay, and so the boundary layer here will be nice and accelerating here, but in this region it starts to get fatter and fatter and fatter, and at some point, I don't know why this note app keeps doing that, it gets fatter and fatter, and at some point it basically separates. It can separate in extreme conditions, and you get a big old vortex here on the wing, and this is an airfoil. And this here is the separation point. And this section here, that is after the separation point, has vastly reduced lift. And so, and this tends to happen at an airfoil as the plane is at a very high angle of attack. And in severe cases, the wing produces so little lift that it can't keep the plane aloft. And it basically starts to fall out of the sky like a rock. Okay, and now I'll discuss a little bit about drag over spheres, cylinders, and other shapes. Okay, and so boundary layer theory captures skin friction, skin but not pressure and drag. But not pressure drag. Okay, so it gets skin friction, but not a pressure drag. And most tables / charts that contain drag coefficients, like there are various shapes, even in the book, you can look at the drag coefficient for a sphere or something like that. Those have the full drag coefficient, which is friction plus pressure, which is usually what you want. So an example of that would be table 9.3. Okay, and now when you use these drag things, like say in table 9.3, pay attention to the Reynolds number ranges and make sure that they're valid. And make sure that they're valid. Now, sometimes you may have a drag coefficient or a drag model for a shape that's valid to a Reynolds number of 10 to the 6, and you're at a Reynolds number of 10 to the 7. Sometimes that is all you have to use, but you just need to be aware that you are, in those cases, you are massively extrapolating a drag model or a drag coefficient data far beyond its strict range of applicability, but sometimes that is all you have and you have to use it anyways. Okay, now the drag over a sphere is such a common shape, it's very well characterized. Okay, and this would be Fig 9.11, and a cylinder, which is similar, is Fig 9.12. Okay, and so for the exact numbers, I will refer you to the book, but here I'm just going to qualitatively draw this CD. This is log scale, and this is RE, and again, this is log scale. Okay, and the drag coefficient for a sphere is not constant. It's a strong function of the Reynolds number, and it looks something like this. Okay, and in this region here, where it is roughly a straight line up to a Reynolds number of about 1. Actually, I drew that a little bit. Is here, this is called creeping flow. And the flow around the sphere is almost symmetric, but there is a net drag even though it is symmetric. D'Alembert's paradox, if you guys have ever heard of that. And here, the line that this forms is the drag coefficient is 24 divided by the Reynolds number based on diameter. Okay, and this is valid up to about a Reynolds number of 1. Is less than 1. Okay, and at a higher Reynolds number, say over here, what we find is that the flow becomes turbulent either on the backside of the boundary layer, and it starts to produce all these counter-rotating vortexes in the wake. And that would be in about this location here. Okay, and now in the turbulent region here, this is at about a Reynolds number of 1,000. And this region here is pretty interesting. And what happens is between this point and this point here is 3 times 10 to the 5th. What happens is that the drag coefficient is essentially constant, but what happens over here is that the drag coefficient suddenly decreases. And if you look at the flow pattern at this point, is that the flow over the sphere actually changes, as that the streamlines, instead of basically going in basically nearly straight lines over the cylinder, actually start to basically turn around, and they start to basically turn back in again. And there's still a very turbulent wake in there. But what happens above this Reynolds number is that the boundary layer itself becomes turbulent. Okay, and when the boundary layer is turbulent, the separation point over here occurs further behind the sphere. And this region here where it's separated has very low pressure. And this low pressure region is actually trying to suck the sphere backwards. And that's a huge and that low pressure region between these two separation points it plays a huge part in increasing the in the drag. And when the flow is turbulent, what happens is that there are some turbulent wiggles, and that introduces some downward motion of the fluid, that it can actually go down around the back of the sphere. Okay, and so that is induced by turbulence. Whereas over here, what happens is that the boundary layer tends to not be turbulent until after the top until the backside, and because the flow is laminar, there is no downward component of the flow to basically help push the streamlines down around the back of it. So instead, the flow separates at the top and bottom of the sphere. So almost the entire back of the sphere is at low P. And so there is a much greater surface area on the backside of the sphere in this region here that is at low pressure, that is actually trying to pull the sphere backwards. And that increases the drag force and the drag coefficient. And then, of course, at these high Reynolds numbers here, as I said before, the boundary layer becomes turbulent here. That introduces some downward momentum that can actually move the separation points down, basically closer towards the center of the sphere. That reduces this area and reduces the region where the very low pressure is trying to pull back on the sphere. Okay, and the drag on a cylinder is very, very similar. Okay, and so this is very well characterized, and the books tend to explain this very well. So I'm not going to go too much more into that. Okay, and then another interesting phenomena that you may have used if you golfed or play tennis is lift on spheres and cylinders. You may be thinking, Ryan, they have a symmetric shape and the flow about them is symmetric. How can they produce lift? Well, usually that's true. So usually flow about a symmetric body is symmetric, which implies no net lift force. Okay, so we have the streamlines are perfectly symmetric. This here is called the stagnation streamline. Okay, and the flow is perfectly symmetric, so there's a lift force that's trying to tug the sphere up from the bottom, or up from the top, and down from the bottom, and they are equal. They are equal and opposite, so there's no net lifting force. However, if the sphere or cylinder is spinning, that's no longer the case. Okay, so the flow will be the flow will be non-symmetric. And you get lift. Okay, and so what happens, so say we have our free stream going in, like this, and our spinning, and a spinning cylinder or sphere, is basically as the cylinder or sphere basically rotates, well, the effect of viscosity is going to drag some of the fluid near the surface along with it. And so the streamlines, instead of being symmetric, they get affected by that, and they actually turn and do something more like this. And the stagnation streamline looks something like this. The streamlines will look something like this, and this is the wake. Okay, and the lift coefficient is in figure 9.7, but qualitatively it looks something like this for a smooth sphere. And these are characterized by a spin ratio by omega d over 2 times the velocity, and that's the spin ratio. And this would be CL or CD, and CD would look something like this. It doesn't vary that much, and the lift coefficient actually has a huge increase at 0 here, and it, oops, I should probably draw that a little more qualitatively correct. Okay, and so basically this explains why if you put backspin on a golf ball, it can actually float a lot longer. And just as a note, if you have the flow velocity going like this and you have top spin, that means the top of the ball or the object is basically rotating into the flow. And the lift is actually down. And if you have backspin, it's the exact opposite. That means the bottom of the object is spinning towards the incoming fluid, and the lift force is up. Okay, and this would be backspin. Okay, and you can see example 9.8 for this. Okay, and one last thing that I will notice that I forgot to mention for the spheres is, I'll go back down again, is if you look at the drag coefficient for a sphere, and again that's on a log scale, log RE, is it looks something like this. This would be smooth. If you roughen the surface of the sphere, in some cases the object may actually have reduced drag. And the reason for that being is because remember what causes this sudden decrease in the drag coefficient is turbulence, basically allowing the flow over the sphere to go down and around and separate basically much closer to the center, and then decreasing the drag. And basically this is caused by the flow in the boundary layer in front of the sphere to start to become turbulent. Well, if the sphere is bumpy, what happens is that the flow in the boundary layer starts to become turbulent at a lower Reynolds number. And so that causes this effect that reduces the area of the low pressure behind the sphere, that causes that area to decrease at a much lower Reynolds number. And for things like golf balls, basically golf balls, if you hit them the flow Reynolds number is actually somewhere in here. That if the golf ball was smooth, the drag coefficient would basically roughly double. And so that has a huge influence on how far you can drive the golf ball. Okay, and so the golf ball, and so ironically, by making some surfaces rougher, in the case of a sphere or a cylinder, you can actually decrease the drag. Now, for a flat plate, a rough flat plate will induce turbulence, and for a flat plate, the skin friction always goes up. Even for this case, where with the smooth sphere, the skin friction always increased with increasing Reynolds number. What decreases is the pressure drag, and specifically that is due to this reduction of the area where there is very low pressure in the wake region behind the object.